Now in this video I'm just gonna explain the application of derivatives. First, let's just look at this function. It's a cubic function. It can be any function, but I'm just gonna give an example with the cubic function. Now, if you look at this function, if you were to draw a tangent line here, you'll have something like this. You'll have a line, and just draw this. You'll have a tangent line intersecting the graph at this point, and you can tell that the gradient of this is positive. And then if you were to have another tangent line from this point, you can draw your tangent line like this. You can tell that here you have a negative gradient. Now, if you were to draw another tangent line here, you were to see that it's negative. And if you draw a tangent line on this point, you were to see that it's positive. But now notice that this function has a turning point here, and it's a maximum. And here you also have a turning point, and it's the minimum. Now what do you realize? You realize that you have a local maximum when a function's gradient changes from positive to negative. And we know that if this function was defined by f of x, then I know that f prime of x, if f prime of x goes from negative to positive, and we're going to check this relationship when f prime goes from negative to positive, or it goes from positive to negative. Now here it goes from positive to negative. You realize that here you have a maximum turning point, a local maximum turning point. And now here the gradient, which is f prime, it goes from negative to positive. Now if it goes from negative to positive, you realize that here you have a local minimum. So that's basically what it means. We call this the first derivative test. This is the first derivative test. Now, what about the second derivative test? Now, you realize that you'll have an inflection point somewhere there. Now, you realize that this function has a slope that goes down. Now, suppose that f at c, let the x value at this turning point be c. Now, if you let the x coordinate at that point equal c, we realize that the first derivative is 0. Now, what does this mean about the second derivative? You can see that the graph slope faces down. This graph, ignore this part. If you ignore this part, then you can see that this slope faces down, meaning that the second derivative is negative. Now, if f prime at c is 0 and then the second derivative at c is negative, then you have a maximum. That's the second derivative test. Now look at this part now. Suppose that f prime at k, let the x value here be k, equals 0 for the turning point. And now the second derivative at k, you realize that here the graph slope faces up. The graph goes up. It faces up. If you ignore, if you take a restriction here, you can see that the graph faces up. That means that the second derivative at that point will be positive, and therefore you'll have a local minimum turning point. So this is just the second derivative test. So that's the second derivative test. That's how you can do this. This is the application of derivatives. Now suppose we have a function defined by the equation f of x equals x into 2x squared minus 8. Suppose you have a function defined with this equation. Now, what are the values of x where the function is increasing, decreasing, or also find the local maximum or local minimum turning points for this function? Now, the first step you have to do is derive this. So you're going to use the product rule here. So the product rule tells you that you have to derive x, multiply that by 2x squared minus 8, and then you add x and you derive 2x squared minus 8. You have to derive that. The derivative of x is 1. Multiply that by 2x squared minus 8. And now derivative of 2x squared minus 8 is going to be 4x. Now 1 times 2x squared, that's just 2x squared. 1 times negative 8, that's minus 8. Basically, you just know this. I'm just showing you that in case this is not 1, it's how you should expand this. Now x times 4x, that's 4x squared. Now notice you have like terms here, and you're going to add them. You'll get 6x squared minus 8. So that's f prime of x. Now you have to get the critical numbers from this. So you equate f prime of x to be 0. That means that 6x squared minus 8 equals 0. And from then you get that 6x squared equals 8. And if you divide both sides by 6, you'll get that x squared equals 4 over 3. Since we have a common factor in 6 and 8. Let me just show you. You have 8 over 6. Now notice that 8 is the same as 4 multiplied by 2. And 6 is the same as 3 multiplied by 2. The 2's will cancel, and then you'll get this. So if you have this, you're going to end up with the solution. If you take the square root of both sides, then you'll get that x equals minus 2 over root 3. Or x equals 2 over root 3. Then there are multiple ways you can solve this. I'm just going to use the number line. It's easier with the number line. You can also use the table method if you want. Then I plot my critical numbers on the number line. Now, I'm going to substitute the numbers below minus 2 over root 3. Suppose I substitute 3 minus 3 here. Suppose I substitute minus 3 to the first derivative. Minus 3 squared, that's 9. 9 times 6, that's 54. And then 54 minus 8, that's 46, so you get a positive answer here. And now I'm going to substitute the numbers between minus 2 over root 3 and 2 over root 3. 0 is between this, so I'm just going to substitute 0. If I substitute 0 here, I'll get 6 times 0 squared, which is 0. 0 minus 8, that's negative 8. You get a negative answer. Now you substitute the numbers larger than 2 over root 3 here. Suppose I substitute 3. So I'll have 3 squared, which is 9. 9 times 6 is 54. Minus 8 will be positive. So now, notice that this graph, it goes from positive to negative. So that's what I just showed you. Like, if the graph goes from positive to negative, that means you have a local maximum. That means that minus 2 over root 3, minus 2 over root 3 is to f at minus 2 over root 3. Root 3. This will be your local maximum turning point. Let me just write local. Then that means that minus 2 over root 3 is your local maximum. And now notice that here it goes from negative to positive. And as I showed earlier, it goes from negative to positive. Then you have a local minimum. So that means that if you have 2 over root 3 here is to f at 2 over root 3, then that means that this will be your local minimum. Now, where is the function increasing and where is the function decreasing? The function is increasing if the first derivative is greater than 0. And the function is decreasing if the first derivative is less than 0. Now here, you can see that the function is increasing since we get a positive answer. And it's from minus 2 over root 3 and less values than that. So that means it's the negative values from this point going all the way to negative infinity. And it's also increasing on this interval from 2 over root 3 all the way to infinity. So where's the function increasing? So the function is increasing. The function is increasing for the interval where x is any number between minus infinity and minus 2 over root 3. Or it's also increasing between the interval 2 over root 3 all the way to infinity. Now, where's the function decreasing? The function is decreasing for x between minus 2 over root 3 to 2 over root 3. The function is decreasing if the derivative is negative. For instance, back in my graph here, you can tell that the graph is decreasing on this interval because that's where we have negative gradients. So that's how you can know where your function is increasing, decreasing, or find the local maximum, local minimum using the first derivative test. Now, let's go back here to this graph. The slope of the graph can be defined with the second derivative. If the second derivative is less than, let me start with greater than, it's greater than 0, that means your graph is concave up. If the second derivative is greater than 0, that means it's concave up. And if the graph second derivative is less than 0, that means that the graph is concave down. That's where the graph slopes faces down. This is concave down, and this is concave up. And you can visualize this graph that from the inflection point up until here, this is where the graph is concave up. And from the inflection point, on this interval, you can see that that's where the graph is concave down. It's facing down. So concave up, concave down, and you can do this for multiple graphs. Let's say I have a graph like this. Yeah. If I have a function like this, where is the graph concave down? You can visualize from this point. This will be concave down from the inflection point. So basically, you just look at the inflection points. You'll also have another inflection point here. And you can see that from this point to this point, it's concave up. So you'll have concave up, and this one will be concave down. And this one will be concave down up until the next inflection point there. So you'll have concave down. Then here you'll have concave up. So I just showed you how you visualize this. But if you cannot use this visual method, you can use the formula. For example, suppose I have sine x. Suppose I have y equals sine x. Then dy over dx. The first derivative of this is cos x. Now, the second derivative of this, will be minus sine x. Now, for concave up, you have to set this negative sine x greater than 0, and then you solve for the values of x for which this graph will be concave up. And for concave down, you set the graph, the second derivative, which is minus sine x, less than 0, and that's where you'll get concave down. So that's how you can solve this with the formula or through visual method. Thanks for watching. Don't forget to share and subscribe.